Well, I'm David Gustavsson. I'm CTO for X-IO here, and I'm going to take you through a little bit of the whole Axellio product. First, I want to start with the philosophy. Why did we do it? How did it end up the way it did and all that, right? Why is it different, if you will? We come from a storage background, and here we are now talking to you guys about an edge computing platform. Quite a different kind of conversation, right? So if we start with, first of all, why did we build a different platform at all today? We talked about earlier commodity hardware. Commodity hardware is a good thing because, well, it drives a lot of volume, it drives down the cost, helps a lot of people, right? The commoditization of hardware also drives a philosophy in architecture that we're going to talk about a little bit later on, around how you solve for very large problems by using commodity hardware. And there's trade-offs in those architectures that really make themselves known in footprint, node counts, power, cooling requirements, all the kind of stuff that happens when you start dealing with really large problems. So in essence, we saw an opportunity as we strategically saw unmet needs outside of the storage area that we traditionally served. So as we started this project, the whole idea was really to build a next generation storage platform. Not surprisingly, right? We started this a long time ago, the next generation hardware. We look at it and say, hey, what are we going to build? What is our next architecture we're going to focus on? And these were really our design goals, right? Breakthrough I/O performance and storage capacity density, right? The faster you can go with more density, the more you can provide to the consumers, right? It's pretty straightforward, be better in the storage side. But to do so, well, we look at technologies that have been addressed with proprietary means in the past. So you've seen a couple of our competitors that have gone down to generating their own flash modules. They go down to managing the flash themselves. They do a very, very good job, but it becomes a proprietary stack, if you will. And you don't get the volumes and you don't get the scales of economy that you would if you use commodity off-the-shelf products, right? So we didn't want to go down the same path and find in the same pitfall and saying, okay, we're going to make a monster box that can do awesome stuff, but because we build everything from the flash die up, it's going to be so costly and we don't get the benefits of scale. So very, very important for us was, let's build something that takes advantage of the technologies that are available in the volume capabilities, if you will. Drives down the cost and allows for capabilities that these proprietary architectures are otherwise trying to shoot for. So there's a couple of influences that drove why Axellio ended up the way it did. It started like a storage architecture philosophy, and as we focused on that, we focused on the I/O subsystem. But the I/O subsystem is only a piece of the architectural needs once you start looking for a bigger who needs the stuff, right? And to us, while Bill explained the edge being you try to essentially put the application where the data is instead of the opposite. And that only happens once you have a certain size of data set, right? It's pretty straightforward. It's easier to move the application than the data, especially today with virtual machines, and you can do vMotions and all kinds of different things to just move the applications around, right? So from a technical perspective, this is probably the best way I know how to explain what we consider the edge. Move the application to the data, then the opposite. And to do that, well, you need to give it architecture enough for power to actually run the application as well, then. Not just run, you know, a low-level storage translation layer, if you will. Okay? So as we look at the market then and say, okay, based on our abilities and what we can do here, and how the market consumes system architectures, there's different types of problems that need different types of architectures. Not all problems are solved the same way, right? As we know in computer science, there's embarrassingly parallel problems, and there's inherently serial problems. And the difference between those two is really how much data dependencies do you have in the subtasks between those components, right? How much data has to be moved between the subtasks to collaborate to come out to a common outcome, right? And what we've seen lately has been a lot of scale-out architectures. Very large scale-out architectures that has been very, very good at certain things, right? So if you look at the different scale-out architectures out there, and scale-out is awesome. It solves really large problems. We talked about earlier, it's fast data or big data. Well, how do you fuse the two today? Well, you put them together in a very large scale-out architecture, right? With a very high-speed network to make this work. But if you look at the scale-out architectures that are out there, there are really two classes, if you will. Either you build a scale-out architecture with orchestration for applications, meaning the applications that run on the scale-out architecture, many of them fits inside a server. It's just that you have so many of them that it becomes a very, very hard problem to solve and architect and manage those applications. So virtual machine-oriented service provider is a great example. Well, all those virtual machines end up running on one machine, right? And then you have the alternative, which is a distributed computing problem, which is your problem is big enough that it doesn't fit on one system. Right? You got to take the system application and slice it into subtasks. And those subtasks then become stripped and spread across nodes. Right? MapReduce is a great example on Hadoop, for instance, where in the end you shuffle the data to one arbiter that sends out the answer in the end. Right? And there's a lot of information that goes back and forth between these nodes. So depending on the problem you're trying to solve, you have an inherent data dependency in the task at hand. Right? And depending on which one you're then architecting for today, well, you end up being very much leaning on the network. The network becomes an intricate part of the compute, right? This is also where we're here. The network is the computer, right? It's because it becomes a larger set together. So what's the alternative to scale out? We all know that. It's scale up, right? What do? You get a bigger boat, right? You build a bigger system that can do more. And scale-up has gotten a bad reputation in the last few years in the market because incremental growth and scaling is a very, very good thing to solve problems that have elastic needs, right? Especially if the application predictability, how much are you going to need, is very hard to predict. Then it's good to buy in chunk size and then grow as you need it, right? Well, not all problems are that way. Some problems, you know, to solve it, you have to have a rack scale architecture just to get the throughput to the needs that you need to ingest, for instance, a certain amount of network ingest, right? So the three problems categories that fall into why does scale-up work better? It really has to do with the nature of the problem. If it can't be sliced into parallel tasks, inherently serial, you can't really slice it into that way. There are particular problems that are just data dependent in a serial fashion, right? Numerical methods, for instance, right? Another famous one is the three-body problem, the sun, the earth, the moon, and how it moves and how they affect each other with gravity. They have a naturally serial-dependent problem, right? So some issues and how these new complex analytics that are being used today have similar type of issues. And then it comes down to where on that spectrum do you fall? Completely embarrassingly parallel to inherently serial. You will have data interchange between the nodes. And the data interchange between nodes can be driven either by the fact that I need to access your data that you hold for me on the data side, or I'm shipping you stuff that are metadata or a result of something I computed, therefore you have to have my data. And all of a sudden, now the data goes onto the network, right? So this now means you start again leaning on the network. So what's happened in the last couple of years? Network has become incredibly competent. RDMA enabled, they go faster, they are very, very fast, right? And they are going down in price continuously and becoming more and more efficient. Turns out, network has a lot of wires, switching, components, chips, translation pieces and such. So if you look at that architecture, there might be a different way to take an approach to this. So in essence, we land in a conversation now where we've got to compare how do you interact and how do you move data? And if it's Ethernet, well, you have certain bounds, you have certain conditions, you have certain costs associated with it. If there's alternatives to move data that are cheaper, faster, and built in already, and you can take advantage of those, you now bring those value add forward that some people can take advantage of. So here we are comparing an internal bus versus an external network. And these things, at first, thinking, well, it makes no sense. Why are you comparing the two? They have very, very different architectural needs or what they are there for. And it's true. But the reason you spill outside of the box, so to speak, is because you can't do enough inside of the box. And the reality is the internal architectural buses in the system have a very, very different transfer rate and the cost effectiveness as well. So if you look at that Xeon CPU today, coming off of the Intel line, every single one of them, even down to the lowest 2603, comes with 40 PCIe lanes, right? 40 PCIe lanes is essentially 40 gigabytes a second transfer rate half duplex. Double that in full duplex in a chip for 200, what, 13 bucks? Try to get a NIC to do that, right? So what you do normally in a scale-out architecture, you then take a NIC and you slap it into one of those slots, and then you extend that network over to a switch. You take that switch, and then you extend it to another card, and it goes into another CPU. Well, there you go. Now you have the translation chain in the Ethernet. And so now, if you can do that cheaper, faster, why not, right? So the challenge with PCIe, though, is that it's an internal bus. And being it's an internal bus, you know, the spec or the guidelines of routing for the traces, no longer than 20 inches, for instance, right? This is a high-speed signal architecture that, let's say it this way, it can be very tricky to get right at large scales. We have some experience with it. And, but if you can make that work, and you can use that bus, you can really move a lot of data for very little extra cost in a completely different realm that we see in network scale-out architectures, right? So it's not that we don't believe that scale-out is, you know, good. Scale-out is awesome to solve very large problems. But if you can solve more in the node, more efficiently, that just helps you a lot better, right? And this goes back to the ever-persistent system integration and put more stuff in a smaller package, because the more of that you do, the more efficient you can solve the problem, right? So we believe in scaling up. We call it scaling in the box, right? Scale in before you scale out. And size the nodes that you're trying to use appropriately for the problem you're trying to solve for, right? Just all using 1U or 2U pizza boxes with, you know, 8-core CPUs, 64 gig of RAM or whatever you do, because reality is, if you don't have enough of I/O capability in that box, having more CPU and memory in that box doesn't help you anything, because you're I/O bound now. So when you're sitting there being I/O bound, having more cores in the same box, all you're doing is sitting around doing nothing. So it's a lot of wasted time, which is also why you see a lot of the scale-out architecture is using very modest type of hardware, right? So where did that lead us? Well, take all these things in combination. Storage company coming at a new platform with new technology capabilities. We're looking at the edge, and what the edge means as what do we need to do to run both the application as well enabling then this I/O capability. And how do we build that in a way that is cost-effective and takes advantage of the technologies in the market such that we get a platform that doesn't cost itself out of being useful, if you will, right? So clearly, we started about 3 years ago on this architecture, believe it or not. 3 years ago, this was before dual-ported NVMe SSDs were available. At that point, everybody was going from 6 gig to 12 gig in SAS, right? We looked at 12 gig SAS and says, yeah, we can go there too. Reality is we're just going to be another me too on that side. So hey, you know what else can? This doesn't make a whole lot of sense. We had really dug in on the NVMe side and recognized the strength of the protocol benefits. And so we started with the system architecture to build a large-scale NVMe architecture, essentially. And then work with some of the SSD vendors out there to make it a dual-ported capability. And the dual-portedness is, of course, important for high availability and for other reasons that we are used to in the SAS enterprise side, right? We used to build our own motherboards. And those motherboards were, I would call them modest in complexity. They were not the complexity that you see in a traditional dual socket, Xeon, full-fledged server architecture, right? And the reason we didn't do that was because, frankly, our software in storage didn't need it. Like Gavin was referring to earlier, we took the SBC1 price performance when we announced our all-flash on a very modest hardware platform because, well, that's what we kind of focus on, getting a lot of performance out of a small package. So we decided to go with the off-the-shelf component approach again, right? So this is actually just leveraging Intel's Xeon motherboards off the shelf. We packaged that then with 72 dual-ported NVMe's. And when we started talking to the SSD vendors around this, because the guys who were working on NVMe at the time saw the NVMe drive being the absolutely upper echelon of performance of SSD capability, right? And why would you ever put 72 NVMe SSDs in one box? That's crazy. By the way, they're rated at 25 watts apiece, right? So do the math. it adds up quite a bit, right? The funny part about that is we actually started with 96 NVMe drives in the box. Ran the power, ran the cooling, got the whole thing designed for power and cooling perspective, everything, right? Just turns out that when you have that many in a 2U system, the box stuck out the rack. No. So, well, it's, we could cool, power it, no problem. Actually, we don't have a problem with that at all.
When the neighborhood browned out, they said stop.
Let me say it this way. If you would take a rack full of these, you will probably have to rethink your power distribution in the data center. What we're seeing is between 2.5 up to 3 kilowatt. Okay? Now, that depends on load, how many drives you put into it, and what you load, what you're configuring the servers and such like that, right? So, while that sounds like a really big number, you got to compare that then to an alternative architecture to solve the same problem. And what we see there is that we're drastically more power efficient, right? Because, well, we don't need all this scale-out stuff. So essentially what happens is, well, you do it internal to the bus, and yes, while you add a few watts into the box, you get a lot more work done. So, another key point, so we designed this box, we put it together, put it in the lab, start working the stuff. We start talking to new breed of customers, right? Like we have had a very in-phase dialogue with a lot of enterprise direct customers using our ICE. That's a storage consumer. And here we are showing something very, very different, and we have a very different dialogue, right? And what became evident is that, well, yeah, by the way, can you put Nvidia GPU in there? Because if you can, I can use my GPU accelerated database on top of this huge data set with a tremendous I/O throughput. And by the way, I have a problem feeding my GPUs with enough data today because I got to go over to a SAN and try to ingest it over the wire to feed my GPU, and I just can't keep it busy enough. All of a sudden, here we are now. We have that much data transfer inside of the box and be able to feed the GPU. So it became evident to us very quickly that, okay, everybody has a different idea on how they're going to use this box. And what we thought people were going to use it for, well, clearly, there's a lot more to it than that. So modularity in architecture, so we can accommodate for different needs, became very, very important, right?
You need to do Ethereum bit mining. What's it?
There you go. That's mostly CPU. Maybe we can do a GPU offload.
GPU. It's low-end.
Yeah, there you go. Yeah. That would be an interesting use case. We should talk after. So, and another point of this, right, is, okay, it's great you have this phenomenal I/O capability inside of the box, but if you can't get the data in or out of the box, then what good is it, right? How many boxes have, actually generates its own data internally? Well, not very many, right? So the point was to, of course, to allow for an I/O path in and out of the box that also serves then incredibly well for scale-out architectures. So it's not limited to be just this scale-up system that can't do anything else, right? So, here's where we landed. Technical specifications on this, right? So a 2U box. The box has, not surprisingly, 2 servers inside of it, right? The 2 servers carries 2 CPUs per. We can go the entire spectrum of the 2600 Broadwell architecture up to 2699, which contains 22 cores per CPU. Multiply it by 4, you get 88 cores, or 176 logical cores, if you will, right? We built it for, of course...
I'm sorry, 4 sockets per
2 sockets
node?
per 2 sockets per server.
Node, 4 sockets per system. Okay,
correct.
Up
to 2 terabytes of RAM. We have ability to add NVDIMMs in the RAM should we need to for fast non-volatile metadata should be needed, used by sophisticated system software sometimes. And then the NVMe storage underpinnings, right? So we do up to 72 2.5-inch NVMe SSDs. Now, it's important there to understand that while the scale has the capability to go to 72, we can scale to any number in between. And we can scale deep, or we can scale wide on that bus in the back end, depending on your capacity versus performance needs, right? So you don't have to start at 0.5 petabyte to play in this game, right? You might start at, frankly, a couple of terabytes and then start growing with it as you need it, right? Some of the performance numbers you see here are...
so it's a multi-tiered structure. You've got NVMe Flash and NVMe SSDs. Is that...
So it's all based on the whole U.2 NVMe form factor. So 2.5-inch standard form factor. which means I can go and find whatever's available in the market, plug them in there just like slots would be in a normal server, right? And that's the whole, a lot of the cost in this architecture is CPU, memory, and NVMe flash. That's really it. And all of them are commodity high volume parts, right? So we can drive down the BOM cost of the entire system. Yes, we have some circuitry and system components, but essentially that's boards, PCBs, right? They're routing the PCIe architecture and how that puts together. The vast majority of the cost sits in all these other components. And that's how we then can keep our costs down and be competitive to, frankly, anybody else that would choose to try to do the same thing. Okay?
Of that 460 gig of NVMe flash, how much is that is actually usable in your system?
So this is, it says 460 gig, 460 terabytes is what it's supposed to be. 460 terabyte. It's all usable. Depending on how you use it then, it'll translate to the software layer as consumable capacity of different kinds, right? So this is raw. This is the raw capacity that is at the lowest layer, right? So when you then boot a Linux kernel on top of this thing, all those devices shows up as /dev/NVMe N1, 2, 3, 4, all those devices. You can then choose to consume those devices in many different ways to create a different layer of capacity utilization, right? So it becomes how much usable capacity do you end up with? Well, it depends on your software stack, right? And that's also where you see us working with system integrators to take advantage of this system, because the reality is most of them come with their own software package, and they want to consume things the way they want to consume things. Okay? So you can see some of the performance numbers we have measured. Over 12 million IOPS. That's a single sector transfer, so arguably useful. As low as 35 microsecond latency. That, I can tell you, changes things.
And you're measuring that from the CPU inside the controller to the storage and back. You're not actually measuring it across the network or anything like that.
The application running to access I/O, right? So the traditional storage latency that you would, because the application is not running inside of the box, right? So it accesses the storage straight inside.
I'm sorry. You measured that where?
At the application layer inside of the system. So the application,
inside the Axellio box, right?
So the application is loaded inside of the system.
Yes.
Yep, and then exactly right. So
what's the networking? You have networking here, but I don't see the specs on the network.
Yep, we can go into that. I have that in the next slide set, so we can go into that. But it's a good question. The optional offload modules here is Intel Phi, Nvidia GPUs, different kinds for different needs, right? Those are, so essentially what we do, since this is PCIe architecture, is that we can translate these NVMe modules into essentially PCIe modules that you just attached and use as what would be a PCIe socket eventually. Okay? So this was kind of the, how we...
Are the NVMe SSDs hot pluggable?
Not in this architecture. We're working on that right now. This is carry forward of integrating deeper, right? So this is SSD carrier, if you will, right? What we're seeing is we had some conversations with solution vendors is, yeah, they absolutely are looking for hot pluggable pieces. So that's exactly what's on the design table right now. Okay?
And so how do you then account for failure in the system then when you start to lose these over time?
Great question. So as you start losing these over time, first of all, our experience with SSDs today is very, very, very different than what hard drives used to be. They don't fail to nowhere close to the same degree. And what we're finding with this customer need, they don't even want RAID. Once you have a big enough data set and you're solving a problem not big enough, then what happens is, in their mind, because they are pushing the system as fast and as hard as they can, that's the only reason you're looking at a solution like this, is that any of that stuff just slows it down. And frankly, what's more important to me is to get the insight than it is to make sure that I cover for this, very, very few occasions where something doesn't work right? So while we are used in high availability storage enterprise requirements, and of course you have to have data protection, you have to have all these stuff. Well, this is a very different marketplace. It's a very different thing. Essentially, right, what we're competing against here is
memory.
Off-the-shelf server with a crap load of memory shoved into it. And they're trying their best to keep the work set in memory. And many times do they fail, so they spill. And as soon as they spill out of memory, they get slowed down an order of magnitude or more because the I/O subsystem is so slow. right? So it's a very different requirement set.
So is it basically operating where they're basically like sharding the data set across all the disks separately, and then just one dies away from maintenance window to replace it?
You could do that, and what we're finding in a lot of the streaming analytics pieces is they put a file system on top of it and in different folders, and you just mount the drives and create the pieces, and the file system just writes them flat. So
Well,
yeah.
If you're competing with memory in this environment, let's say, a 35 microsecond latency is pretty
No,
hard.
that's orders of magnitudes higher than memory.
Yeah. So I mean,
Yeah.
do you find that customers are willing to deal with?
Well, so that's
additional-
why you also have the ability to go to the memory that you need in this architecture, right? So you have 2 terabytes of RAM in this. So we're not saying don't use memory. It's just that when you go outside of memory, which you will inevitably do if you do complex analytics, right, and large data sets, when you do, don't be bound by an old single SSD or hard drives in the system, right? If you can feed memory at these type of rates, it changes how the whole solution has to come together, because a lot of the scale out then is, okay, let's keep everything in memory, right, and short it out. And if it's an embedded paralleling problem, that works really well. Some of them are not, right? So this is, I'm not saying this is going to take over every scale-out architecture. By no means. We are not trying to solve
General purpose.
hyperconverged scale-out problem, being a general-purpose VDI scale-out problem, right? Talk about embarrassingly parallel. Everybody has their own desktop, and you can run how many on each node, and you just add another one you need to. And the cross-communication between the two, well, that's usually on the data set because of the distributed file system sits underneath that hyperconverged architecture, right? In this architecture, everything is internal. Everything is needed to, if you need to get to data at large speeds and large masses, it's right there at the fingertip.
So the trick is, if the data set overflows RAM, I can have half a petabyte.
That's
Where
right.
traditionally, instead of having 35 microseconds, I'd be looking milliseconds if I had to start even on a good, well-designed scaled system.
Yep.
So
And in some of those scenarios, right, there's very, very smart algorithms in what you keep in memory versus what you keep on disk, which means the philosophy there is, the way we have done that in the past is what? Large transfers, sequential, because that's how you get high transfer rates. Why do we do that? Well, because the drive can either read fast in sequential or write fast in sequential. If you do both at the same time, what happens? It falls off the cliff, right? Because now you have a contention point. So a lot of software out there too have not taken into consideration the fact that you actually have now completely bidirectional capability in this data pool where you can read it as fast as you can write it and at the same time. And this is where you see this new breed of solutions start cropping up regarding real-time analytics while ingesting. While before, a lot of the packet capture architecture was essentially find a way to peel off all the packets off the Ethernet wire without losing a packet. So if you look at the architectural focus on a lot of those companies today, what they did was build a NIC. And they have a NIC that has an internal buffer on it so they can peel off the packets and then destage out of that buffer into memory, right? So essentially the problem was, how do we get it off the wire? Well, now when they can't get it off the wire fast enough, now it's a matter of getting it into disk. And now once it's in the disk, how do you make something useful out of it? So now the next cycle here is elevate your stack to do analytics on top of the same data set.
Seems to me this would be a perfect use case for some 3D memory once that really becomes a viable product.
Perhaps.
Optane.
Perhaps.
Exactly.
There's absolutely, what this does, it is radically changes the I/O, CPU, memory balance. It changes how you think about how you solve problems. Because essentially what we've done is eliminated the I/O bottleneck. Mm-hmm. And the I/O bottleneck many, many times in the architecture drives why it looks the way it does. Okay?
Up until this point, a Hadoop architecture took a number of different devices, a number of different storage plays, and compute elements. Seems like you're putting an entire Hadoop architecture in one 2U rack.
So, Hadoop, MapReduce. You have a large data set, and then you keep it on many, many nodes. You need to traverse the entire data set to get some insights out of that data, which essentially then becomes, how fast can I read that data set? So what do? We take a set of drives and put them in a node. We take another drive set and we put it in a node. And you know, with today's server architecture, depending on what drives you put in there, you'll end up where somewhere probably between 1 or 2 gigabytes a second read capability in that system, right? Well, this gives you 30 times that.
Right.
So it is definitely a tool to be used deliberately to solve problems that today scale-out problems are solving, just not necessarily elegant. Okay? And I think that that kind of concludes the introduction and why we ended up with what we did. Okay? So I think we're going to transition to the next stage here, and talk about a little bit about what's going on inside of the system, right? How did you do this? What is it really, right? And how did this come about in a way that we reach these numbers? And we got into some performance numbers as well as system architecture pieces. So we saw this before, design objective. We started with a philosophy of trying to build the next generation storage architecture, realizing that we need a lot more than just storage and capability in this system to solve for these real edge case that we're talking about. We landed on this architecture. We talked about the capability and what's inside of it, and what it can hold, if you will. A big part of this design drawing here that you can see is Fabric Express, as we call it. It's essentially our internal bus that we have put together to make this possible. And the whole idea behind Fabric Express is, like we said, PCI Express is a lot faster and cheaper and built into everything to move a lot of data fast. So let's take advantage of it in a way that gives us these benefits, right? So taking a look at a PCIe and an NVMe, which is really the heart that drives a lot of these I/O capability of this subsystem, right? Do a bit of a primer on PCIe to start with, right? It's been around forever. Everybody knows the term. Not everybody digs into the details and the underpinnings of PCIe per se. It's a serial bus that has a transmit and receive that creates a lane, essentially. You then have those lanes ganging up in parallel to create a link. You can have a by 1 to by 16. The spec actually takes it all the way to by 32, but today's architecture, you see it top out mostly in by 16s, right? 8 gigatransfer a second, that means that it's 125 picosecond bit timing, right? So these bits fly really fast, and there's a lot of them running there, right? Each lane adds up to about almost a gigabyte a second in each direction. So full duplex in one lane is 2 gigabytes a second. That's all built into the chip right there, right? And we haven't really exploited all of that. So we're like, okay, let's expand on that. So essentially, 1 by 16 link gives you close to 32 gigabytes a second full duplex. And every CPU comes with it, and you're not paying any extra for it. NVMe, software side now. Okay. Intel was a really big proponent in driving the NVMe standard. Many of us recognize now why. Because they started the NVMe protocol stuff a long time ago. And the reason for it is because if you have a media that you can access really, really fast, and you have a protocol that sits on top of that media, that takes up a vast majority, if not, frankly, at this point, we talked about 3D crosspoint media earlier. And if you're going to do 3D crosspoint accessible media over some storage interface, you're literally spending 90% of your time traversing the Linux kernel, block drivers, controller architectures, right? This is where this doesn't work. We got to break it up and do something different. This is where really a lot of the NVMe impetus came from, right? We got to create a protocol that allows for the flash performance of the capability to really come through. Right? So the NVMe architecture rethought a lot of the whole I/O streaming and such, right? While the SAS and the SATA protocols had their focus on developed during the hard drive era, had its ambitious goals of the time, but just not good enough for what was going on anymore. And this is where the NVMe now comes in. So what's different about NVMe is that it is massively parallel. 64,000 queues, 64,000 entries per queue, which allows for a completely lock-free distribution of those I/O queues between the cores to give you a very low latency, high performance API. And on top of it, it is a very, very lean protocol. It is less than half the CPU cycles for every I/O. So not only is it massively parallel, but every I/O in turn also takes a lot less time inside of the CPU, right? And well, the software latency that you lower by doing that is also impacting the end target. So if you have a SAS device, well, that controller, the SAS controller that's going to sit in that SSD, has to do the same protocol handling. So the controller also becomes busy doing a lot more work. So you improve latency tremendously, right? So here's the protocol comparison we did when Intel wanted to. So Intel announced their dual-ported NVMe drive a year ago. They came out and said, hey, look at our DC 3700, I think it was, is what they called it. And essentially, we have a dual-ported NVMe drive. We had built the system while they were building the device in parallel. We launched first kind of preview of our system at that time. And here's the SAS versus NVMe protocol impact that we ran on our system, right? And what we're seeing is roughly 6 times difference in lower latency, which of course immediately translates to 6 times higher IOPS, right? So these are radically impactful, right? So the whole idea is there's a tremendous benefit of using NVMe over PCI Express rather than 12 gig SAS, if you will. So what's this Fabric Express actually? So we take the motherboards and we extend the native PCIe bus that comes out of the motherboard into our enclosure such that we can take advantage of those lanes and attach these devices to it. So we have 6 modules essentially. These 6 modules hold up to 12 drives each. That gives us the 72 drives in the system, right? And you can populate those drives, frankly, in any way you want. So if you want a lower capacity, I should say, because by the time you spread across all the data packs, if you will, or the SSD carriers here, they are adds up to becoming, 24 drives anyway, right? So it depends a little bit on how you want to configure it, but it allows us to populate them according to the need of the application, right? And it also ties the both server nodes together. That allows us to run inter-node communication over the same bus. Very low latency, very high bandwidth, right? And it also allows us to memory map each other's spaces. So we can do very low latency application semantics that does not have to take the latency of going down the Ethernet stack, out on the wire, over to the other guy, up the Ethernet stack again, and then talk to the network, right? Now we're talking low-digit microseconds to communicate between the 2 servers for metadata transactions or whatever needs to be, right?
So the 2 servers, that's strictly for HA, or is that for load balancing across?
Sure. Since it's a hardware box, you could use it any way you want. We built it clearly when we started the project with the intent for high availability, right? A high availability storage architecture that needs to have a mirroring bus for the write-back cache. Very straightforward, right? We use the PCI Express to mirror the data back and forth. Turns out, well, the PCI Express bus can also be virtualized in a software layer to become an Ethernet bus. Software doesn't know any different. It just goes over the Ethernet or PCI Express very, very quickly. So if you have a server cluster, for instance, if you want to run a clustered logical volume manager or something like that with a transactional database on top of it, now you can have a transactional database with, double-digit microsecond access to the entire half a petabyte of the pool for the database, right? 2 clusters nodes in the same box, and all of a sudden, right, you don't need a SAN for shared data on the back end for the entire thing, right? So we also see 2 different nodes being used where one node has a certain purpose. Like I talked about before, data ingest is a hard problem when you're trying to do it fast enough on the Ethernet. And mainly it's a hard problem because management packets on the Ethernet wire, 64 bytes, they're small. And when you can stuff 40 gigabit on that wire, you can divide by 64 and see how many of them it is in a second. That's a hard problem to solve. Mm-hmm. That's why you see buffers on the cards and all that kind of stuff, right? So in those scenarios, it becomes essentially a networking probe dedicated to do nothing but peel the packets off the wire. And you can't do much else on that node. So that node now is dedicated to do nothing but take the data, put it on the media. Now you have a node right next to it that shares the same data set that you can do now fun stuff with. You can read the data, you can do analytics, you can do real-time stuff. While the other guy is writing, you can do this, right?
I can see how that
Dave,
solves a problem. Gus?
Go ahead.
I'm sorry, Ray. But clustering software, do you have something in place to make, say, one of these devices does go down, a failover to the other to handle the compute layer?
Right. So we rely on the software layer. In our case, when we get there and put our software on it, right? Clearly, we take care of that, right? Now, let's say that you have a cluster database It's a shared storage backend.
No, I'm really talking more about a hardware cluster. Because a lot of the time the failover takes, particularly when the data is flowing at this kind of transfer rate, really interrupts the operations of the processing, of the ingest.
Right.
Is there a cluster management software that takes that sort of down to a very short?
So we rely on, if I understand your question correctly, let me try to answer it. We rely on the clustering software that is available in whatever application you're running today. So let's take, in the case where you have one server running ingest and the other one doing analytics, there is no redundancy in that system. Right? Should you have one of those go down, you lost that capability. So what we've seen when we have talked to those use cases is, well, we have two systems and they do it in parallel. Should one go down, the other one keeps going. So that's what kind of their redundancy level, right? The alternative architecture that you're working with today is a server doing nothing but ingest, right? Put it on the wire, and by the time you actually want to do something, it's after the fact kind of thing. You say, oh, something went wrong yesterday. Let me go and suck out the information that is inside of that box from yesterday and do a forensics at that point. You don't get no real time at all today, right? So it's not necessarily, and by the way, yes, they have two systems running side by side doing that today because should one go down, the other one takes over anyway. So it becomes a redundancy by independency, if you will, right?
A failover isn't something necessarily you guys provide. It's something you allow your partners to develop on. And
exactly. But it's possible to use on this architecture because of the shared data set. Right? So the dual ported nets architecture allows you to create a failover because it's a shared data set. Okay?
What's the offload modules as part of the Fabric Express do?
That's the GPUs.
Oh.
So the offload modules allows for...
So those offload modules could be accessed from either server then?
So in this, you have the two middle flash packs there contain GPUs. Those offload modules are essentially an extension for compute offloading, right? So you connect those into this architecture if you need more CPU. So if you look at how much CPU can you cram? Well, you know, of course, there's extreme architectures out there that cram tremendous amount of cores in a small footprint. Well, that's not really what we're trying to do. What we're trying to do is give a lot of CPUs that are cost-effective,
balanced with the rest,
coupled with this very large data set, right? So 2699s, 88 cores, 176 cores is a lot of CPU, believe it or not, right? It's actually a tremendous amount of CPU. That CPU gets you up to 3.6 teraflops, right? That's including turbo boost and all that stuff in there. Now, one Nvidia V100 is about 15 teraflops. Two of those in there, you have multiplied your math capability, essentially, by 10. Right? So it's no wonder that we're seeing a very, very ferocious appetite for these offloading systems in the servers today, especially for very heavy computational architectures, right? So if you can figure, the drawback, of course, is, well, you got to write software to take advantage of it, and there's not a generic API that you can just drop software on top of it and it runs 10 times faster. No, you have to actually understand your problem. You have to code against this hardware to take advantage of it. But what we're seeing in the market today, right, which is also evident by Nvidia stock, a lot more and more is figuring out how to do this effectively, right? So networking, 16-lane PCIe per server for networking. So that's a dedicated by 16 lane. This allows us to do, 2 by 100 gigabit per server easily, right? We can go even faster, but the point there is we can attach these to a very high speed network architecture as well. And yes, it can take the same RDMA enabled NICs that you see that the networks are starting to take advantage of today, right? Yeah. And that means that the software architectures for applications out there that takes advantage of those drops on, runs just like it would on any other server. Okay? We have given the ability to do a full height card in there as well. And the reason for it is because what we're seeing from these network capture architectures is that the form factor of those NICs are bigger than what the traditional half-height cards are, because while they put ASICs on there, they sometimes put FPGAs on their cards and such, so they need a bit more space, if you will. The SSD carriers, like I said, hold 12 drives per carrier, up to, and each is 25 watts. That's 300 watts in a carrier from a, let's call it spec number, right? And the GPUs are 300 watts per GPU by the spec. So it's very symmetrical when it comes to, are you running 12 drivers or are you running 2 GPUs in a double wide? So from a power and footprint perspective, right, this balances very, very nicely. And we have then made these pluggable modules interchangeable that way. Make sense? Yeah. Any other questions so far? So here's some performance numbers. Small block transfers, 4K, 100% writes, 30 gigabytes a second at 4K transfers. 7.8 million IOPS, and you can see the lowest latency, 35 microseconds, goes up to 90 microseconds where we hit our 30 gigabytes a second. On reads, 33.7 gigabytes a second, bit over 8 million IOPS, and a little bit higher latency. Part of the reason for the write latency being lower than read latency is, well, these SSDs also have a write cache that is, you know, faster to media, so the read latencies goes up a little bit, okay? Large transfer.
I'm sorry, David, could you go back to those graphs?
Sure.
For a second. The IOPS numbers there are, those are 78, like the first one, 78K, 7.8K are doing 30 gigabytes, 30 and a half gigabytes per second, because they're big.
Right, so
they're big IOPS.
We hit 7.8 million IOPS. Latency,
Oh, it's million.
90 microseconds
Okay.
at 30 gigabytes a second.
Yeah, it's million IOPS, okay.
Once you saturated the link, yeah.
Right, you saturate the bus, and once you saturate the bus, you ain't gonna go any faster, right? So you can see we hit the saturation on the 4K there. On a larger transfer, 128K, we saturate the bus pretty quickly. QDEF1, we hit almost 36 gigabytes a second on reads, on writes, right? And we hit that at essentially at QDEF2 on the reads, right? And here's the beauty about the PCI bus. It's full duplex. So I can do these two at the same time. And yes, we don't get perfectly twice because there's some overhead when it happens, but we're seeing well north of 60 gigabytes a second at full duplex.
Could you go back to the prior one again? Sorry, I need to do this here. Thank you, come on.
Okay.
And it's 4K random reads and random writes that you're doing here. It's not
Correct.
Sequential or anything like that.
Correct, no sequential, nothing. It is uniform random. Okay?
Yeah.
And it turns out, if you do sequential or random, it makes a little difference.
It makes no difference?
Makes a little difference, a little. But
Could you go to the next one then?
very little. Now, you can see the latencies on these are a bit higher.
Yeah.
And it's also because, well, it's a lot more data to transfer in one transfer, so now you essentially stack these transfer back to back, right? Okay, so we talked about this use case. This is edge data analytics, right? Before, it was very hard. It was doable, but very large architectures were needed to have a very high-speed ingest, store the data at the same time you're trying to run an analytics and provide insights, right, for a large enough data pool. The only way you could do this, essentially, was a very large scale-out, slice the problem into smaller chunks, and find a way to have an simultaneous access to the data store. So you've got to store it on a SAN now, which has shared access, right? The only way to get it to SAN is to have a very fast SAN to get to these numbers. We know a company that went out and tried to solve that problem, right? DSSD went out and tried to do exactly the same thing, but attached to servers to do the same thing, right? And the numbers, not quite the same, but very similar when it comes to how much data we can move in those ways, right? The difference is we really built this out of volume, commodity parts, to keep the cost down such that it can be cost effective in the industry. So, to recap, 2U, converged server to storage, very different converged than the hyper-converged idea people have in their mind as a scale-out architecture, right? This gives you a very, very different use case in mind, right? High-performance analytics processing, large persistent in-server NVMe data store, very high bandwidth, and, you know, clearly capable of taking our storage software and do something really cool with it down the road. Any questions?
You didn't talk about.
There was a reflex of, do I really want to know how much this might cost?
So, I mean, you didn't talk about NVMe over Fabric or anything like that. It's
Yeah, I did.
potentially possible because you've got the networking to do that sort of thing.
There's nothing prohibits us to participate in the same NVMe over Fabric enabled hardware capabilities, right? You take an NVMe over Fabric enabled Mellanox card or so, put it on the front end, and all of a sudden, what do you have?
And the storage, I'll call it personality, runs in Linux, or what's the operating environment?
So most of the stuff that we talk to, most of the customers and solutions that we talk to are Linux oriented, very many of them. Now we have started to talk about some interesting use cases, taking Microsoft and Storage Spaces Direct on top of this architecture, because it essentially gives you a hyperconverged software stack out of the box, right?
Yeah.
And if you can imagine an RDMA-enabled Ethernet between boxes of this capability using that software, there's a very powerful scale-out architecture story there, right?
And the storage software that you runs at kernel mode or user mode or?
No software.
I'm sorry?
No software. You boot Linux, it shows up as /dev/NVMe, the same inbuilt into Linux kernel. So it's absolutely nothing but just
What about the write-back mirroring and all that stuff?
That's all done in the drive. Individually in the drive. They have their own write caching inside of the drive. Essentially, this is take the data out of the Linux kernel as fast as you can, shove it down the drive because it takes care of the rest, and you're done.
So if I wanted to use some kind of software layer data protection, do Linux double RAID?
Absolutely. So you have logical volume managers, you have MDADM, you have all kinds of different things in software that can take advantage of it, right? Now, clearly, to your point, Ray, is there opportunities to take this architecture and provide services and layers on top of it to provide either kind of capabilities? Absolutely, right? And what you will see here in the talk here soon, it will be one of the things that we anticipate we can add services with has to do with how you shrink the data set with dedupe, right? Okay?
So before Gus finishes, Eric, I want to address something you just said about price.
Yes.
So I don't want to go into exact pricing because we could be on a rat hole, but if you were to go to a large, well-known server and storage, recently joined company, and spec up a server with an equivalent amount of just standard flash, you're probably going to be around the same pricing. A little bit fraction more for this, but we're not talking crazy money. When you look at some of the things that specialists are out there like DSSD, this is a fraction of the price. So yes, it's not cheap, but it's not actually surprise you how cost efficient.
Yeah, all the costs in the flash anyway, right?
The reality
I
is
was about
this.
to say,
If you need to solve a problem of this magnitude, you're going to have to solve it somehow. Any alternative architecture that has the need for this type of flash and performance will be more expensive. I can guarantee you that right now.
If you build it out of traditional architecture,
That's exactly
you
right.
will be more expensive. You just got more boxes, more PSUs, like everything.
Exactly.
So is there going to be reference architectures to go to said server storage architecture company and build this stuff, layering the Axellio software on top of it?
So there's a lot of interesting conversations going on. We'll see where it takes us. Right now, we are trying to help those who have this need solve their need as a system integrator. You saw Gavin's slide on how we take this to market right now, and that is frankly through providing this as a platform for those companies to take it to market, right? And as that develops, I wouldn't be surprised that conversations develop as well.
It's difficult for us not to think 2 steps ahead.
Yeah, totally understand. Totally understand.
So,
okay. Yeah.
Can I ask one more real quick? I guess I'm kind of the VAR partner guy in the room, but do you see this as being sold to, integrators to figure out how to wrap their stuff around it?
Very much.
And so do you see this being sold by your standard VARs and trying to figure out how to do a Splunk solution out of it or something else?
I would assume that would develop towards that. What we're seeing is people that have really tough data problems to solve are knocking on our doors and saying, hey, I heard about this thing. Can we have a conversation? We sit down, have a conversation. It usually starts with a POC. We run some tests, figure out how they're going to take it to market, right? And depending on their routes to market, right, we then work with them on that.
Yeah, to me, this is a really interesting platform. It's very different than what I expected to hear when I walked in. But it's going to be a really hard message to control properly, I think.
Yes.
And be careful how you
And this
go
is why I
about that.
emphasize, is this hyper-converged? Well, I guess depends on what you think is hyper-converged, right?
It looks like,
right?
But the use case is really different.
Yeah, exactly.
And the reason for it, because hyper-converged today are applied where it's very easy
Parallelized
to scale out because the problems they're trying to solve for are, like we talked about, embarrassingly parallel, right? And we believe that we can solve those problems more cost effectively if you have a big enough problem as well, because the reality is just the infrastructure cost alone in some of those large deployments are tremendous, right? So we're going to start by solving some really tough problems and then move on from there. I think